Good afternoon. Just looking at what we have been working with regarding functions. And again, we looked at functions on an individual basis, and then we have crossed over to equations in the XY coordinate system, and we also will be looking at operations existing between functions. And just going back to what we have in section 1.5, okay, there was a set of items to be looking into, and we have for problem number 6. Okay, now we're looking at going back to the point slope as well as the slope intercept formulas. And we have in this particular problem, okay, it says to write an equation of the line that have the given conditions and to write the answer in slope intercept form if possible. Okay, so we have with the description of this line. Okay, it is said to pass through the point with the coordinates 4, -6, and the line also has a slope that is equal to 3. And so looking at trying to write the equation in slope-intercept form, okay, we have for the backdrop that is utilizing the point-slope equation setup. Okay, and again, we have for the point-slope formula, again, we have y minus y of 1 is equal to the slope m times the quantity of x minus x of 1. And we have the values of the slope as well as the coordinates that we're going to be plugging in at hand. And for what we have, first of all, okay, so we have with 4, -6. Again, all ordered pairs are of the form xy. So we'll say that we have 4 is x of 1 and -6 will be representing y of 1. And again, we have the value of the slope at 3. Okay. And so just looking at substituting what we have here. So we have y minus y of 1. In this case, we have y minus -6. And we have is equal to the slope m, which we have again given at 3. And we have times the quantity of x minus x of 1, again, where x of 1 is at 4. And just for the slope-intercept equation, okay, y minus -6, we have y plus 6 is equal to, again, 3 times the quantity of x minus 4. So this part is the point-slope equation, but I want to write and translate out, okay, to the slope-intercept form. Okay, so we can continue, and the object is going to be to isolate y. And I can proceed by eliminating the parentheses. Okay, so upon distributing 3 over the quantity of x minus 4, I'm going to have that y plus 6 is equal to 3x times, okay, and we have 3 over -4, okay, so that's going to be -12. All right, so I have y plus 6 is equal to 3x minus 12. And looking at isolating y, so I'm going to take 6 away from both sides. And so we will have, for the slope-intercept form, okay, we come out to y is equal to 3x minus 18. And you can go back and check. So we had the slope-intercept form, and again, the coefficient alongside x is going to be the slope, so I have m at 3. And again, I can test out what we have with y at -6 and x at 4. So left-hand side of the equation is going to be -6, and I want the right-hand side to be as well. Okay, so with x at 4, we have 3 times 4 is 12. 12 minus 18 is -6, and -6 is equal to -6. And just looking at what we have, at least from a visual perspective, I think I do have this one up. Let's see. I got it somewhere. Let's see. Oh, I thought I had it. Yes, I do. Okay, so we have for the graph, okay, so you have y is equal to 3x minus 18. Okay, so we have a positive slope with 3. So the line would be proceeding upward as we read from left to right. And again, for y is equal to 3x minus 18, 4, negative 6 is among the points, okay, through which the line is going to pass. Okay, now we have for the next item, okay, and we have for number 12, and we're looking at establishing the slope-intercept equation of the line, okay, that's going to pass through negative 4, 8, and negative 7, negative 3, okay. And now, unlike number 6, I do not have the slope given, but instead I have 2 points provided, okay. And so before we can get to the point slope formula backdrop, I'll need to be able to identify what the slope is. Okay, and so kind of taking that extra step of finding out just what the slope is going to be. Okay, and again, just back from the initial proceedings and looking at equations in the variables x and y. Okay, so we had the determination of the slopes. You had the change in y with respect to change in x. And again, where x1 and x2 are not equal to each other, and looking at finding out just what the slope of the line is going to be that passes through negative 4, 8 and negative 7, negative 3. And again, it doesn't matter what you have to be your first and second x and y values. Just keep in mind that all ordered pairs are of the form x and y. Okay, so we'll say that negative 4 will be x of 1, while a will be y of 1, and for the second x and y values, okay, we have negative 7 and negative 3 respectively. Okay, so filling in, okay, so for y of 2 minus y of 1, so we have negative 3 minus 8, and for x of 2 minus x of 1, we have negative 7 minus negative 4, and negative 3 minus 8. Okay, so we have negative 11, and negative 7 minus negative 4. This translates to negative 7 plus 4. So right now, I'm going to have a ratio of negative values. Okay, so I have negative 11 over negative 3. Negatives will cancel. So the slope is going to be a non-integer value, okay, in the amount of 11/3. Now, for what I have in creating the point slope backdrop, I can choose either ordered pair. Again, it doesn't really matter which you choose. Okay, so for the point slope setup, okay, and I'll do here, I'll just go with negative 4, 8. Okay, so for the point slope setup, okay, so I have y minus y of 1 is equal to the slope m times the quantity of x minus x of 1. Okay. So we have in the proceeding. Okay, so if I choose negative 4, 8, so I'm going to say I have y minus 8 is equal to, and we had the slope m, and we determined that to be 11/3. Times the quantity of x minus x01, and x01 we have at -4. Okay, so we got in what we have for the point slope equation setup. Okay, so right now we got y minus 8 is equal to 11/3 times the quantity of x plus 4. Okay. Now, looking at following through and putting things in terms of the slope intercept equation. So just transferring over. Okay, so again, I determined the slope to be 11/3, and I could have chosen either ordered pair, and I went with -4/8 in the point slope setup. So I got the point slope equation. Now I'm looking for the slope intercept equation. So we have y minus 8, and now distributing 11/3 over the quantity of x plus 4. Okay, so I have 11/3 of x plus 44/3. And looking at isolating y, okay, so I'm going to add 8 to both sides. Okay, so we have here, okay, so you got y is equal to 11/3 of x. Now for what I have in the case of 44/3 plus 8. So I have 44/3 plus 8/1. And just raising 8/1 in terms of thirds. Okay, so 44/3 plus 8. Okay, so this will be 44/3 plus 24/3. Okay, so this will come out to 68/3. All right, and arriving at the sum, and it's going to turn out that for the slope intercept form, we're going to have that y is equal to 11/3 of x plus 68/3. Now, and looking at what we have now, okay, so again, for the slope intercept equation of this line, we have y is equal to 11/3 of x plus 68/3. And if I put in, see the graph on this one, okay, so I have y is equal to 11/3 of x plus 68/3. And again, among the points through which the line will pass, again, we had the stated -7, -3, and also -4, 8. And just like the line in number 6, okay, since the slope is positive, it is going to proceed upward as you read the graph from left to right. Okay, all right. Now, in the crossover again to looking at parallel and perpendicular line characteristics. Okay, now we have for numbers 23 and 26. Okay, we have, first of all, okay, we're just looking at the determination of slope. And in part A, okay, for number 23, okay, it says to determine the slope of a line parallel to the given line if possible. And again, for 23, okay, for part A, Okay, for the parallel line, parallel lines are going to have the same slope, and if the given slope is 11/3, well, the parallel line is going to have a slope at 3/11 as well. And for part B, in the case of the determination of the slope of a line that runs perpendicular, okay, now again, parallel lines will have the same slope, whereas in case of perpendicular lines, okay, you're going to have an opposite sign reciprocal value. So here, from 3/11, going from a positive to a negative, and the reciprocal of 3/11 is going to be 11/3. Okay, so the slope of the perpendicular is minus 11/3. And again, the product of the slopes of perpendicular lines will be -1. Okay, so again, you have like 3/11 times -11/3. Again, 3 times 11 is 33. 11 times 3 is 33. But a positive times a negative is a negative. And so, again, the product of the slopes will be -1. Okay, now, for what we have in the case of 26, again, we're looking at the slope of a line parallel. If the given slope is -10, well, for the parallel line, we have -10 likewise. And for the perpendicular, okay, so we're going from a negative to a positive, and the reciprocal of 10 is going to be like the reciprocal of 10/1. And so that will be 1/10. You can always go back and check. So you have -10 times 1/10, or -10/10. And so this, again, will have a product of -1. All right. And so again, parallel lines have the same slope, and perpendicular lines have slopes with opposite sign reciprocal values. All right. Now, in looking at relationships between lines, and we have for this particular pairing, it says to determine if the lines defined by the given equations are parallel, perpendicular, or neither. And for what we have in the case of 32, we have with these two lines, okay, the first one we have 2x plus 3y is equal to 7. And for the other line we have 4x is equal to -6y plus 2. And to determine if they are parallel, perpendicular, or neither, okay, we need to determine just what the slope values will be. Okay, so for 2x plus 3y is equal to 7, okay, I can determine the slope upon expressing in terms of the slope-intercept form. So I can initiate by getting 3y by itself, and looking at taking 2x away from both sides. So we have 3y is equal to -2x plus 7. And as I express in terms of y, so I can divide the equation terms out by 3. And so we have for that slope-intercept case, you have y. It's going to come out equal to -2/3 of x plus 7/3. Okay, so for the first line, we'll have that the slope m is equal to -2/3. Now, looking to see how this sizes up with respect to the second line. Okay, now we have this in the form of 4x is equal to -6y plus 2. And just like the first equation, I want to express what I have here in terms of the slope-intercept. Okay, so I can start out getting the y term by itself. I can just move the 2 over by subtracting. So right now I've got 4x minus 2 is equal to negative 6y. And if I just reposition things, kind of like taking the commutative property of equality, like transitioning from the parallel to b is equal to a is equal to b, I'm just going to swap sides here. Okay, so I have negative 6y on the left, 4x minus 2 on the right. And now expressing in terms of y equals, I can divide the terms all out by negative 6. And for what I have here, so I got negative 6y over negative 6. So this becomes y. And 4x over negative 6. So we have an x term. Now 4 over negative 6 will be negative 4/6. And this will be reducible where we have negative 2/3 of x. And what's going to be negative 2 over negative 6, this will be a positive 1/3. And we have the slope to also end up at negative 2/3. Okay, so in terms of distilling kind of the main points in establishing the relation. Okay, so you have in this setup so you have the same slope, and notice you have different values for b. So you have same slope, different y-intercepts. And with these two characteristics interlocked, okay, this is going to signal that the lines are parallel. Okay, so we do have with these, so 2x plus 3y is equal to 7, and 4x equals negative 6y plus 2. You notice, okay, these lines are parallel. They're proceeding in the same manner, but they are distinct from each other and will thus never intersect. All right, and again, parallel lines never do intersect. Now, for what we have in the case of setting up equations for parallel and perpendicular lines and intertwining with, once again, the point slope and the slope intercept forms. And we have for the upcoming exercises, it says to write an equation of the line with the given conditions and to express the answer in the slope intercept form if possible, and also in standard form with no fractional coefficients. Okay, now we have for number 37, now we have that the given situation is going to be looking for a line that passes through 2, 5, and it's going to be running parallel to that line, which is defined by the equation 2x plus y is equal to 6. Okay, so looking for a parallel. So parallel lines again will have the same slope, and whatever slope I'm having for the line that passes through 2, 5, I want it to have the same slope as the given line. And framing things where I can find out what the slope is going to be. Okay, so we have with the given line. Okay, so you have with the equation, okay, and this is in standard form, and I can arrive at the slope-intercept form. So right now I have 2x plus y is equal to 6. And I can get the y term by itself rather quickly upon taking 2x away from both sides. And so we're going to have that y is equal to negative 2x plus 6. So we have the slope-intercept form. So for the given line, we're going to have that the slope m is equal to negative 2. For what we have in the case of the parallel line, again, we have with the details. Okay, so parallel lines will have the same slope. And we have the parallel line described as passing through 2, 5. And just setting things up through the point slope equation algorithm. Okay, so you have y minus y1 is equal to the slope m times the quantity of x minus x of 1. And so we have filling in. So we have y minus 5 is equal to, again, we have with the slope m, so we have negative 2 times the quantity of x minus 2. Okay, so this is the point slope equation. And looking at distributing, okay, so we have y minus 5 is equal to negative 2x plus 4 and getting y by itself. And we have upon adding 5, so we're going to have that y is equal to negative 2x plus 9. Okay, so that would be the slope-intercept equation. And this other part, it was talking about just the standard form with no fractional coefficients. This is where you had the x and the y terms on the same side. And so if I have the x and y terms on the same side, I will move the 2x over. So I have 2x plus y is equal to 9. And you can always go back and check the forms. Okay, so again with x at 2 and y at 5, we have 5 is equal to negative 2 times 2 is 4, negative 4. Negative 4 plus 9 is equal to 5. And with x at 2 and y at 5 with the standard form, 2 times 2 is 4, 4 plus 5 is equal to 9. Okay, so this will check out. And again, we have the lines to be running parallel to each other. Okay. And again, 2, 5 is among the ordered pairs through which we have the parallel line to be running through. All right. Now, in the case of number 39, okay, where 37 was looking for the parallel line, 39, okay, we're looking at the perpendicular line. And for 39, okay, we have looking for the line that passes through 6, -4, and is going to run perpendicular to the line that is defined by x minus 5y is equal to 1. And so for what we have for the given line, okay, so you have for that standard form, okay, so you have x minus 5y is equal to 1. And just looking at rewriting this equation in slope-intercept form, okay, so if I just move the x over, so now we're going to have -5y is equal to -x plus 1. And getting in terms of y equals, okay, so we have with division by -5. Okay, so we had that y is equal to 1/5 of x minus 1/5. And so we'll have that the slope m is equal to 1/5. Okay, now for the line that's going to run perpendicular, again, not the same slope value, but opposite sign reciprocal. So yeah, the slope of the given line is at 1/5. Now for the perpendicular line, the slope is going to be -5. And for the point through which the perpendicular line passes, okay, we have at 6, -4. And so we have the tools at hand to be able to create the point slope equation backdrop. Okay, and being careful with the substituting. Okay, so for y minus y of 1, okay, we'll have y minus -4. We have is equal to the slope m, and we have at -5. We have times the quantity of x minus x of 1, where we have x of 1 is going to be at 6. So again, your point slope equation, we have y plus 4 is equal to -5 times the quantity of x minus 6. And proceeding to get to the slope-intercept and the standard forms. Okay, we have, we're distributing -5 over the quantity of x minus 6. So we'll have the right-hand side at -5x plus 30. And getting the y term by itself. Okay, so I can take 4 away from both sides. And so in this outcome, okay, we have for the slope-intercept, we'll have y is equal to -5x plus 26 okay, so this will be the slope-intercept equation. and we have with the same line, okay, expressing the equation in standard form, again with the x and the y terms on the same side, we have 5x plus y is equal to 26. So just looking at it again, so we have a y at -4. Okay, we have for x at 6, -5 times 6 is -30 plus 26 is equal to -4. And 5 times 6 is 30. Y is -4. 30 minus 4 is equal to 26. Okay, so the values do check out. And just providing this one more visual. Okay, so we have these lines to run perpendicular. So the given line we had at x minus 5y is equal to 1. And again, the perpendicular, again, we have passing through 6, -4. And again, the slope-intercept expression, we have at y is equal to -5x plus 26. And again, perpendicular lines will meet in a right angle or 90-degree fashion. All right, now, for what we have regarding functions, okay, there is the ones we have by and large looked at have been running continuously, but you might have those functions that can be broken up into separate sections, and we kind of looked at that, especially with some of the vertical line test cases. And for what we have in the case of functions, and there is one group, and this will be what is referred to as piecewise defined. Okay, and just like for piecewise defined functions, okay, like an example could be like tax brackets on a federal return. Okay. And for piecewise defined functions, okay, say if you have like going, so you can have a given function f of x, and how the output ends up following through or being arrived at is going to be contingent upon the nature of the input. And let's say that for a piecewise defined function, we say that for a value y is equal to f of x, we say that it is equal to, we'll say, -3x plus 4 if, let's say, we have that x is less than -2. Okay, just for the values x that are less than -2. But now for other values in x, we can say that f of x is equal to, we'll say the absolute value of x if it turns out that we have it that -2 is less than or equal to x is less than or equal to 7. And we'll say that we have f of x is equal to, we'll say, x squared minus 2 if we have that x is greater than 7. Let's say that for this function. So if I were to determine, we'll say f of 6, and we'll say we have f of negative 3, and we'll say we have f of 10, and also with the numbers that are repeated in our statements concerning x. Okay, so you have this given piecewise defined function. Okay, now for what we have, first of all, okay, so you have for f of 6. Okay, now 6 is going to be the value of x. Okay, now if you notice where 6 is going to belong, okay, in terms of which of the inequalities the input belongs. Okay, so 6 cannot be greater than 7. So we're not going to apply x squared minus 2. And also, we cannot have that 6 is less than negative 2. So we cannot use the negative 3x plus 4 part. But with 6 being between negative 2 and 7, and since it is true that negative 2 is less than or equal to 6 is less than or equal to 7, so this statement for the input is going to be true. So in terms of which of these three categories we're going to be utilizing for f of x, it is going to be the absolute value of the input. So f of 6, okay, for the follow through with x at 6, we're going to choose the absolute value function. So we have f of 6 is equal to the absolute value of 6, which is going to be only 6. Now, for what we have in the case of f of negative 3, okay, now, again, negative 3, not greater than 7. This time it is not between negative 2 and 7, but it is among the input values less than negative 2. So you have the first inequality description to refer to negative 3. And so since the first inequality applies, we have the first leg of the f of x portion to be the output approach. So in this case, with f of negative 3, that is going to be negative 3 times negative 3 plus 4. And negative 3 times negative 3 is positive 9 plus 4. And so this comes out to 13. Okay, now for what we have concerning f of 10, for f of 10, okay, so you have 10 is greater than 7. So x is greater than 7 is the inequality that fits. But now what do I do with 10? I'm looking at the expression in front of the inequality. So now we'll be looking at the square of 10 minus 2. And 10 squared is 100. And we have 100 minus 2, so this will come out to 98. Okay, now, if you notice with negative 2 and 7, okay, those are mentioned twice. And looking carefully at the inequalities. So for f of negative 2, okay, now, you know, so we don't have the equal sign here. So negative 2 cannot be less than itself. So the first inequality does not apply. And if I try the next inequality, okay, so you have negative 2 less than or equal to, negative 2 is less than or equal to 7. Now negative 2 is less than 7, so the upper end checks out, and we have at the lower. While negative 2 is not less than itself, it is equal to itself. And so the compound inequality will fit the bill for the input value of negative 2. And since the inequality, the compound inequality works, we're going to have, again, f of negative 2 is going to be equal to the absolute value of negative 2, and the absolute value of a negative becomes a positive. And we have for f of 7, in this one case. So for 7, notice we have with the inequalities containing 7, if x is 7, well, I cannot use this last function since 7 cannot be greater than itself. But for the compound inequality, now 7 cannot be less than itself, but it can be equal. So to say that negative 2 is less than or equal to 7, which in turn is less than or equal to itself, that is going to be true. So I'm going to have the compound inequality to be that to which the input value of 7 belongs. And just like what was the case with 6 and negative 2 as the inputs, I'm going to apply once again the absolute value function portion. Okay, so f of 7 is going to be equal to the absolute value of 7, and the absolute value of 7 is going to be 7 itself. All right. And tell you what, just for what we have concerning function values, and just before I leave parallel and perpendicular lines behind altogether at the moment. And say we determine the equation line that runs through 3, 2, and is perpendicular to the line defined by x plus 3y is equal to 5. Okay, and for the equation of the line, we'll just look for the slope intercept. And also for piecewise defined functions, we'll say we have given f of x is equal to x plus 2 if x is less than negative 1. Let's say f of x is equal to the constant value 33 if negative 1 is less than or equal to x is less than 6. we'll say the f of x is equal to, the absolute value of x is, if 6 is less than or equal to x is less than or equal to 10. And we'll say that we have for the rest, we'll say that f of x is equal to x plus 20 if x is greater than 10. And let's determine what we have for, let's say, we have f of 6, f of negative 1, and let's see, let me throw this out here. So you have f of 10, f of negative 4, and f of 21. Okay, so for the next few moments, let's see what slope-intercept equation of the line we get for the first item. And again, with the piecewise defined functions, let's see what 5 functional values we get, okay, from this piecewise defined function, and we will discuss in the next few moments. Okay, so looking at the piecewise defined function first, okay, so you have 4 separate sections, and here we have looking at the determination of f of 6 to begin with. Okay, so for f of 6, again, your x value is at 6, and to determine among which of these inequality descriptions, okay, negative 6 is going to belong. Okay, if you notice, we have 6 as a limit value expressed, okay, for the second and third inequalities. Now where 6 belongs, well, if you have x at 6, well, 6 cannot be less than itself, so the second inequality, or the compound inequality, goes out. But for the third inequality, okay, so we have 6 is less than or equal to 6 is less than or equal to 10. Okay, now, again, 6 cannot be less than itself, but it can be equal. And in turn, 6 is at least less than 10. So the inequality description to which the input value of 6 belongs for x is going to be where we have 6 is less than or equal to x is less than or equal to 10. And so with that being said, okay, the function that appears alongside will be that which I have to apply. So we're back to the absolute value of x, where x is at 6. And we have the absolute value of 6 is going to be 6. Now for the next input value, okay, we now have at negative 1. Now like 6, okay, negative 1 is a limit value which is expressed more than once among the inequalities. Now for negative 1 cannot be less than itself, but it can be equal to itself. So to say that we have negative 1 is less than or equal to itself, and in turn negative 1 is less than 6, that statement is true. So you had the second inequality to apply, and guess what? Anything that is between negative 1 and 6 in this fashion is going to result in a constant function where we have f of anything between negative 1 and 6 in accordance with the compound inequality described results in the constant value of 33. So we have f of negative 1 is equal to 33. Okay. Now for the next inputs, okay, we have with x at 10, and for f of 10, okay, to see where 10 belongs among the inequalities. Well, 10 cannot be greater than itself, but it can be equal. Yeah, 6 is less than or equal to 10. That is true, since 6 is less than 10. And while 10 cannot be less than itself, we do have the equal sign where 10 is equal to 10. And so just like what we had with 6 earlier, we're going to have the absolute value function portion of f of x to utilize. So we're going to have the absolute value of 10, which is 10 itself. Okay, now for f of -4, okay, and for the input of -4, well, -4 is the only value in the set that is less than -1. So -4 is less than -1, so we are referencing x is less than -1, and the portion of the function we'll be utilizing is going to be f of x is equal to x plus 2, whereupon x is at -4. So we're going to have -4 plus 2, and -4 plus 2 is equal to -2. And for what we have in the case of f of 21, well, out of the inputs, we have here 21 is the highest, and it is among the inputs greater than 10. So 21 is greater than 10, so we are referencing x is greater than 10. And in terms of the output, with the input at 21, well, the output is going to be 21 plus 20. And so whenever x is at 21, we have for the corresponding y value, this will come out to 41. Okay. All right. Now, for what we have in looking for the slope-intercept equation of the perpendicular line, and we have, again, so we have with the description, okay, so the perpendicular line is going to run through the ordered pair 3, 2, and it's going to be running perpendicular to the line described by x plus 3y is equal to 5. Okay, so we have for the given line, I want to find out, okay, just what the slope is going to be. Okay, so I have x plus 3y is equal to 5. And if I rewrite this equation in slope-intercept form, okay, so I can isolate 3y upon taking x away from both sides. Okay, and so we have 3y, 5 minus x, or having x, the x term out of the front. We have 3y is equal to -x plus 5. And then expressing in terms of y, if I divide the terms all out by 3, so we have that y is equal to -1/3 of x plus 5/3. Okay, and so we have with the given line, okay, again, the x term coefficient is -1/3. And now for the perpendicular line of interest. Okay, and again, perpendicular lines will have opposite sign reciprocal slope values. So the given line has a slope of -1/3, whereas for the perpendicular, we're going to have a positive reciprocal of 1/3, which in this case is going to be 3. So we had the slope is at 3, and the point through which the perpendicular line passes is going to be 3, 2. Okay, so looking at setting things up, okay, to get to the slope-intercept equation. Again, we have through the point-slope pathway. Okay, so you have the slope as well as the coordinates of the point. We have 3, 2. So for y minus y01, okay, so this will be y minus 2. And we have the equal to the slope m, which is 3, times the quantity of x minus the value of 3. Okay, so this is our point-slope equation. Now setting things up, okay, where I can finally get to the slope-intercept. So distributing 3 over the quantity of x minus 3. So we have y minus 2 is equal to 3x minus 9. And then we have upon adding 2 to both sides. And so we'll have here that y is equal to 3x minus 7. Okay, so the slope is going to be at 3. And for what we have, just checking for the consistency, so we have with x at 3. 3 times 3 is 9. 9 minus 7 is 2, is equal to y, which is also at 2. So we do have consistency. All right, now, there was a problem where we had like a curve, and you had a straight line that was going through it, and it said to find the slope of the line that was going through that particular curve. And now just kind of going back to situations of this type, this is going to be what is going to be referred to as the average rate of change of a function. And this is just like a formalized way of determining slope. And for what we have regarding the average rate of change of a function, okay, so you have the average rate of change of a function. And which refer to the function as f of x, or as y is equal to f of x. So you have the average rate of change of a function between 2 points. Say the first point, okay, now in functional notation terms, you have x of 1, f of x of 1. But essentially what this is, it's just another way of saying x of 1, y of 1. And the second point, we have with x of 2, f of x of 2. Which is the functional notation counterpart to what is essentially x of 2, y of 2. And the average rate of change of function between these points, okay, and you have this slope variable m, and now I have SEC subscripted, okay, and the SEC, this is in reference to the slope of the secant line. Like a secant line is just going to be connecting 2 points of interest, okay, that happen to be on the graph of the function, okay. And for the slope of the secant line, okay, so you're looking at, again, vertical change with respect to horizontal change. So like f of x of 2 minus f of x of 1 over x of 2 minus x of 1. But again, just in terms of our common terminology, okay, you're still looking at y of 2 minus y of 1 over x of 2 minus x of 1. And again, whereupon you have the x of 1 and x of 2 cannot equal each other. Okay, so we're not interested in the secant line being a vertical line. Okay, now, and to give you kind of a setup here for average rate of change, okay, it's kind of like a formalized functional notation counterpart to just determining slope, which it essentially is. And let's say that, okay, just to kind of give you an example. And let's say that if we have given y is equal to f of x is equal to x squared plus 2x so y is equal to f of x is equal to x squared plus 2x and we were to determine the average rate of change and we'll say have say like we have for part A, so we have from x equals 1 to x equals 5, and then we have second, and we'll keep the same initial point. So you have going from x equals 1 to x equals 9. Okay, so we're still looking for slope. Now I have all these x values, and to be able to determine slope, I need corresponding y values. Okay, and now for what we have, again, we have this given function. So for all your values of x, your y values will be attained, okay, through taking the square of x plus 2 times x. And let's say now for our x values of interest, we have 1, 5, and 9. Say if I'm looking at what we're going to have for the y value whenever x is equal to 1. So the y value whenever x is at 1, okay, that is going to be f of 1. So you're looking at 1 squared plus 2 times 1. Okay, so 1 squared is 1. 2 times 1 is 2. and 1 plus 2 is equal to 3. Okay, so we have with 1 point, okay, so you have 1, 3. So 1, 3 is a point on the graph of this function. Okay, now looking at what the corresponding y value is going to be whenever x is at 5. Okay, so substituting accordingly. Okay, so x squared plus 2x now is going to be 5 squared plus 2 times 5. Okay, so we have 5 squared is 25. And 2 times 5 is 10. And we have, for the output, okay, we have whenever x is at 5, okay, y is at 35. Okay, so you have the y value when x is 1 as well as when x is 5. And we'll go ahead and get to the y value whenever x is at 9. So if x is at 9, so the y value have 9 squared plus 2 times 9. So 9 squared is at 81. And 2 times 9 is at 18. And 81 plus 18 okay, have coming out to a rather high value at 99. Okay. Now, for the average rates of change, okay, so just going between the x values from x equals 1 to x equals 35. Okay, what you're looking at essentially is that in terms of going from one point to the next, okay, from x equals 1 to x equals 5, you're looking at going from 1, 3 to 5, 35. And for what you're going to have in terms of the, again, for the average rate of change, that's going to be the slope of the corresponding secant line. Okay, which is still comes down to the slope formula. Okay, so you have for y2 minus y1. And then we have just substituting accordingly. Okay, so you have with the arrangement, let's say that 1, 3 is x1, y1. 535 will be that x of 2, y of 2. And filling in for the values. Okay, so y2 minus y1. So we have 35 minus 3 for the change in x. So x of 2 we have at 5 minus x of 1. So you have 5 minus 1. Okay, so overall, okay, you have a vertical shift of 32 units while having a horizontal shift of 4 units. But breaking it down incrementally, you're looking at like an 8-to-1 ratio. So the average rate of change in this case is going to be at 8. So that is between x equals 1 and x is equal to 5. Okay, now, and just going out further. Okay, now we're still with the same initial point. Since we're beginning from x is equal to 1, but this time we're going out further to x is equal to 9. So again, at x equals 1, okay, we have the point at 1, 3. Now going out to x equals 9, we're going from 1, 3 to 9, 99. Okay, so we got the same first point. Now the second point is now 9, 99. This time filling in, so y2 minus y1. This time we have 99 minus 3. For x2 minus x01, so we have 9 minus 1. Okay, so this time we have a vertical shift, vertical change of 96 units, and for the horizontal change, okay, we have 8 units, and we have 96 over 8. And so 8 is completely divisible into 96. Okay, for the average rate of change, okay, we come out to 12 units. Okay, so you have different rates of change, okay, throughout, okay, and just looking at what we have for the nature of the activity occurring. I think we got it, yeah. Okay, so just taking a section of what we have for the quadratic function. Again, for this particular curve, again, it's just a small section, but for this red curve, okay, so this is in reference to y is equal to f of x. Is equal to x squared plus 2x. And for the line I have in the blue as well as the green, okay, notice you have from 1, 3 to 535. Okay, that is going to be the secant line passing through the function and intersecting at 1, 3 and 535. Again, for the slope of that secant line, that is equal to 8. Okay, so the slope of this line is 8 units. Whereas if I go out further, branch out further to x is equal to 9, so the 2 points of intersection you have with 1, 3, and this time we have at 9, 99. And we have with the slope of this particular secant line, again, that is going to be at 12. And with the behavior of the graph of this function, it's like the further out to the right you go, the higher the elevation is going to be, and so you're going to have the average rate of change is going to continue to increase. Like if I went out to x is equal to 10, 12, 20, even 100, you can expect the slope of the secant line to be running up continuously. Okay, so increasing ever so much more. All right, so this is what we have with average rates of change, and it still comes down to just what we commonly refer to as like the slope of a line passing through 2 points. All right, now again, I had mentioned at the start that we will be looking at operations between functions. Okay, so we looked at functions individually. Now looking at we might have more than one function involved, and where we have operations to exist between them. And we'll just call this part, okay, where we have operations between functions. And for what we have for operations between functions, okay, we'll be looking at the first four types. Okay, and the first four, there'll be the more basic variety. Okay, so you have first kind will have what we refer to as the sum function. And give you a bit of an introduction here. So for what's going to lead up to the sum function among the other operations. Okay, say we have for functions f of x and g of x. And you could be working with more than just two functions, but we'll just keep it to just two functions in the general case. Now we have what's referred to as the sum function. We're going to have f plus g of x. And that can be written as the sum of the functions f of x and g of x. And we have next in line, along with the sum function, we're going to have the difference function. And you could have the letters in either order. But if I have it as f minus g of x, and we'll write this as the difference between the functions, we're going to have that which is put out to the front. Since f, I had it at the beginning, we had this at the front, and with minus g to follow, rewriting the difference function as the difference between functions. So f minus g of x becomes f of x minus g of x. And for what we have in the case of the product function, okay, so we have f times g of x is equal to f of x times g of x. And then we have with the quotient function, so we have with f over g of x. Okay, so this comes down to f of x over g of x. All right, now just as a case for what we have for operations between functions. And we'll say that we have f of x is equal to x minus 2 and we'll say that we have g of x is equal to let's say we have 4x plus 3. Okay, and if I'm looking at, let's say, for the operational functions, okay, let's say we have in the first case, like specifying, okay, like what would be f plus g of x? Okay, so we have with f plus g of x. Okay, so we have, again, in the general case, so we're looking at f of x plus g of x. So specifying, so we have f of x with x minus 2. We've got plus g of x, okay, which we have at 4x plus 3. And just taking out the parentheses. Now I just label parentheses just to itemize f of x apart from g of x. So I got x minus 2 plus 4x plus 3, and combining like terms together. So I have x plus 4x will come to 5x, and negative 2 plus 3. Okay, this will come out to a plus 1. So f plus g of x becomes 5x plus 1. Now if I have, let's say, f minus g of x, for f minus g of x. Okay, so this comes down to f of x minus g of x. Okay, so we're still working with the same functions. So I have the quantity of x minus 2 minus, okay, we have again minus all of 4x plus 3. Okay. Now, for f of x minus g of x, so f of x, we still have an x minus 2. Now the subtraction of g of x, we're looking at subtracting all of 4x plus 3. So 4x and 3 will become negatives. So this will translate to negative 4x minus 3. And combining the terms together, okay, so we have x minus 4x becomes negative 3x, and negative 2 minus 3 becomes negative 5. So we end up at negative 3x minus 5. Okay, now let's say that if I change it up, I'm going to have mentioned, okay, like what if I were to switch the order? And say if I had g minus f of x. In this case, if I had g out at front, well, between the functions, I have g of x to be deducting f of x. So for the dynamics that will be played out, so we have g of x, again we have 4x plus 3, and we have subtracting f of x. Okay, so right now g of x, no sign change, so I still have 4x plus 3. But for f of x, since it is being subtracted, okay, you have everything pertaining to f of x. We'll have the terms to change signs. Okay, so we're going to have negative x, and subtraction distributed over negative 2 is going to change over to the addition of 2. So we have 4x minus x becomes 3x, and we have 3 and 2 become 5. So this comes out to positive 3x plus 5. And notice we have an additive inverse here, where we have positive 3x and positive 5 as opposed to a negative 3x and a negative 5. Now for the product function, okay, so for f times g of x, okay, so we're looking at f of x times g of x. Okay. So for f of x, so I have x minus 2 and again I have times g of x, so I'm multiplying by the quantity of 4x plus 3. And what I can do here is I can just FOIL out the terms. So I'll just work down. So the first product we have with x times 4x. So this will be 4x squared. Outside term we have positive 3x. Inside product negative 2 times 4x. So this will be a negative 8x. And negative 2 times 3 comes out to negative 6. And so we have 4x squared, and combining like terms in the middle. So we have 3x minus 8x becomes negative 5x. So we have 4x squared minus 5x minus 6. And for what we have in the case of the quotient functions, okay, so you're going to have in the layout, okay, so you have for f over g of x we have f of x over g of x. Now f of x, we have x minus 2. And for g of x, we have 4x plus 3. And other than 1, there's no common factor that is shared between the numerator and denominator. And if I reverse, it'll just be the reciprocal. So if I have g over f of x, so this will be g of x over f of x, where you just have g of x is going to be at the top. In this case, we have 4x plus 3, and that's going to be all over f of x, which we have at x minus 2. Okay. Now there is a remaining portion, okay, that we're going to have regarding domain. And let me mention, okay, so we have and copy this and just mention some things about this regarding domain. Okay, so you got your sum, difference, product, and quotient functions. Now, for these three items, namely the sum, difference, and product functions, okay, so we have the sum, difference, and product functions. They're going to have the exact same domain. Okay, so the sum, difference, and product functions will have the exact same domain, which will be formed by combining the exclusions or I should say exclusions or restrictions. So formed by combining restrictions, if any, of f of x and g of x. And for the quotient function, this could be potentially the odd character out. And the reason for this is that we have a fraction in the quotient function, and for fractions the denominator cannot be 0 in value. All right, and okay, so just to mention, okay, so we have with these items, okay, and I'll give you like a case here. Let's say if you have and we'll say that we have f of x is equal to 3x plus 7, and g of x is equal to 4x minus 8. Okay, so I have to determine the domain of f of x g of x as well as what we have for the operations. Okay, so we have looking for just the domain. So if I'm looking for the domain of f of x equal to 3x plus 7, okay, notice, okay, we don't have a fraction, we don't have an even root radical. So there's no restriction. Okay, so for f of x, you're going to have for the domain, you're going to have the set of all real numbers. And for g of x equal to 4x minus 8. Okay, so you have like f of x, we have a linear function. And guess what? No fraction, no even root radical, so you have no restriction. And like f of x, g of x is going to have a domain that is going to consist of all real numbers. Okay. Now for the sum, difference, and product functions. Okay, now the sum, difference, and product functions will have the same domain, and this can be formed by combining the restrictions, if any, of f of x and g of x. Well, guess what? F of x doesn't have any restrictions, nor does g of x. Okay, so we have in the case of the sum, the difference, and the product functions, there are no restrictions because there were none for f of x or g of x. And guess what? So that means that throughout, okay, like the individual functions, the domain of the sum, difference, and product functions will be the set of all real numbers. Okay, so automatically you didn't have to get to the sum, difference, or product function expressions because again the domain is defined by combining the restrictions of f of x and g of x. And since f of x has the domain at all real numbers and g of x likewise, that rolls over to the sum, difference, and product functions. But now in terms of where you actually had to operate to define what the domain is, that's going to rest upon the quotient function. So we had the restriction that the denominator cannot be 0. Okay, so for f over g of x, just kind of working over to what we have here. So we have for f over g of x, so we have f of x over g of x. And again, so f of x we have at 3x plus 7. And for g of x, okay, we have 4x minus 8. And guess what? Okay, this is, since the denominator cannot be 0, okay, we do have an imposed restriction for the quotient function. And that is that 4x minus 8 cannot be 0. So we had that 4x cannot be equal to 8, and thus we had that x cannot be equal to 2. And so we have, just from a visual perspective, so we have with the quotient function, again, being sort of the outlier. Okay. Again, we have the restriction that x cannot be equal to 2. And it's the only function out of the bunch, okay, that has a restriction. So x cannot be 2. So x cannot be 2. Okay, and so you have 2 is excluded. Again, just for the values that will be in the domain will be those values, so less than 2 and those greater. And so it's going to follow that for what we have for the domain of f over g of x. So you have that instead of all real numbers. Okay, you have just broken up into the union of subintervals. So we have at the lower end, we have those values of x less than 2, as represented by the ray going to the left and bypassing 2, and we have for the other part, then we have those values of x which will be greater than 2. And again, we have in the interval notation, we have parentheses around 2 and infinity.